Welcome to the Substation Primary Design course, expertly crafted by engineer Sharif Hussain, designed for engineering students and professionals. This video represents part 3 of our comprehensive earthing calculation series, delving into detailed grounding system calculations specifically for L-shaped electrical substation layouts operating below 66 kV. In this session, we will meticulously walk through a practical step-by-step example for designing safe and effective grounding grids that effectively mitigate dangerous touch and step voltages during critical fault conditions. Our detailed example is based on a practical L-shaped substation layout, measuring 100 meters by 60 meters with an extending arm of 40 meters by 20 meters, which is a common configuration that demands precise grounding design considerations. The essential key input data required for these precise calculations encompass the substation layout dimensions, a comprehensive soil resistivity report, and details on the surface layer type along with its specific resistivity values. For instance, in our practical example, we utilize a soil resistivity value of 40 ohm meters, complemented by a surface layer thickness of 0.1 meters, as derived from field measurements. The primary required outputs from our rigorous calculations include the optimal grounding conductor cross-section area, the precise number of ground rods needed, and the calculated tolerable limits for both step and touch voltages. Additionally, we determined the critical ground potential rise, denoted as GPR, the E-mesh voltage if applicable, and the important E-step voltage to ensure comprehensive safety analysis. Several key estimations and constant parameters play a crucial role, such as the ground resistivity measured in ohm meters, which is directly determined from the detailed soil resistivity test report. Surface layer resistivity values are typically set at 3,000 ohm meters for asphalt surfaces and 5,000 ohm meters for gravel surfaces, influencing the overall safety tolerances significantly. The shock duration time is conservatively assumed to be between 0.5 to 1 second, serving as a vital factor in all personnel safety calculations for fault scenarios. We strategically estimate the grid conductor spacing at 7 meters throughout the layout and incorporate 80 ground rods, each precisely 7.5 meters in length, for optimal performance. The ground grid is installed at a typical depth ranging from 0.5 to 1.5 meters below surface, while also extending 1.5 meters beyond the substation boundary to enhance safety margins. Other important parameters include a current division factor of 0.7 originating from the substation boundary and a decrement factor of 1, applicable for the entire fault clearing duration. Specifically for a 110 kV substation, we assume a substantial short-circuit current of 40 kA, which is a key value used in determining the appropriate conductor sizing requirements. A pivotal step in the process is calculating the minimum size of the grounding conductor precisely using equation 10.14 from established standards. This essential equation precisely evaluates the minimum conductor cross-section area in square millimeters, directly as a function of the maximum conductor current during faults. Among the variables, the symmetrical ground fault current if in Ka is critical, and for the National Grid Saudi Arabia system, it corresponds exactly to the breaker-rated short-circuit current value. Tm stands for the fusing temperature in degrees Celsius, representing the absolute maximum allowable temperature that the conductor material can safely reach during a fault. Ta denotes the ambient temperature in degrees Celsius, while alpha_r is the thermal coefficient of resistivity for the conductor material at the reference temperature Tr. Rho_r refers to the resistivity of the ground conductor material at the reference temperature Tr, measured in microohms per centimeter for accuracy. The maximum possible clearing time, Tc, is conservatively taken as 1 second to account for protection system response in real-world scenarios. TCAP is the material-specific thermal capacity factor sourced from Table 10.1, quantified in joules per cubic centimeter per degree Celsius. K0 is mathematically defined as 1 divided by alpha_r, or alternatively as 1 divided by alpha_r minus Tr, expressed in degrees Celsius for thermal modeling. Tr serves as the reference temperature for all material constants, ensuring consistency and reliability across the entire set of grounding calculations. Applying these precise parameters in our example calculation yields a required conductor size of 150 square millimeters specifically for the 40 Ka fault current scenario. Table 10.2 offers recommended ground copper conductor sizes tailored to various fault current levels for practical implementation. For the main ground grids, it recommends sizes after performing the detailed calculation. The final selected conductor size should always be the nearest higher option from the recommended table to guarantee enhanced system reliability. This conservative approach ensures the conductor can reliably withstand intense thermal stresses from fault currents without ever exceeding its critical melting temperature limits. Ultimately, these rigorous and methodical calculations are absolutely vital for safeguarding personnel safety by maintaining touch and step voltages strictly below their tolerable safety limits. This part of the course focuses on the critical aspects of designing safe grounding grids in electrical substations, strictly adhering to IEEE STD 80 standards for personnel protection during fault conditions. We will cover key calculations including grid potential rise, or GPR, maximum grid resistance R_G, and the tolerable touch and step voltages, all essential parameters outlined in the standards. Understanding these parameters is essential to prevent shock hazards during fault conditions, ensuring the safety of personnel working in or around high-voltage substations. First, let's define the reduction factor for derating the nominal value of surface layer resistivity, denoted as C_S, using equation 10-6 from IEEE STD 80. C_S equals 1 to 0.09. C_S equals 1 when there is no protective surface layer, but it is less than 1 if the protective layer, such as gravel or asphalt, has higher resistivity than the underlying soil. Next, we consider the thickness of the soil protective surface layer, H_S, measured in meters, which plays a key role in derating calculations for surface materials. The duration of the shock current, T_S, is in seconds and is typically set to 0.5 seconds for National Grid Saudi Arabia applications, representing the fault clearing time. Resistivity of the surfacing material, ρ_S, typically ranges from 1,000 to 5,000 ohms for materials like gravel, while ρ is the resistivity of the soil beneath it. Now, let's calculate the tolerable step voltage, critical for safety limits. These calculations incorporate the C_S factor, soil resistivity ρ, surfacing resistivity ρ_S, and shock duration T_S to determine safe voltage limits for human exposure. For our example, with specific values like ρ_S equals 3,000 ohms, H_S equals 0.7 meters, ρ equals 40 ohms, and T_S equals 0.5 seconds, C_S calculates to 0.694. This C_S value leads to a tolerable E-step of 2,213 volts and a tolerable E-touch of 676.4 volts, representing the maximum safe voltages for 50 kilogram personnel. Next, we calculate the grid potential rise, or GPR, using the straightforward formula GPR equals I_G multiplied by R_G, as per equation 10-2. Here, I_G represents the maximum grid current in amperes during a fault, and R_G is the grid resistance in ohms, both vital for GPR assessment. The grid resistance R_G is calculated using equation 10.13, which involves the average ground resistivity ρ, grid area A, total buried length of conductors L_T, and grid depth H. For substations, the ground resistance should ideally be 1 ohm or less to ensure safety margins. The current division factor S_F relates the total fault current to the portion flowing through the grounding grid via I_G equals S_F times I_F from equation 10-8. For National Grid Saudi Arabia, the minimum S_F value is 0.7 unless specified otherwise in the project technical specification. I_F is the breaker short circuit rating, representing the maximum fault current that the system must withstand during ground faults. Now let's apply these calculations to a practical example based on real substation design parameters. Given specific dimensions and resistivity values, the total buried length of conductors L_T is calculated as 2,331.28 meters for this grid layout. The substation area A is 5,600 square meters, with an average soil resistivity ρ of 40 ohm meters and a grid depth H of 0.5 meters, excluding any asphalt. Using these input values in equation 10.13, the grid resistance R_G is calculated to be 0.252 ohms, which is below the 1 ohm target. With a maximum grid current I_G of 28 kiloamperes, the GPR is then calculated as 28,000 amps times 0.252 ohms, yielding 7,080.8 volts. Comparing this GPR of 7,080.8 volts with the tolerable E-touch of 676.4 volts, we see that GPR greatly exceeds E-touch, indicating a potential hazard. This indicates that the current design is not safe yet, and further analysis, such as calculating the maximum mesh voltage mesh, is required per IEEE 80. Such situations necessitate a redesign, perhaps by expanding the grid or adding more conductors, to ensure maximum E-touch and E-step values stay within tolerable limits. The mesh voltage, denoted as E_M, is a key parameter in grounding grid design, represented by the equation _M equals ρ times K_M times K_M times I_G, all divided by L_M. Here, ρ represents the soil resistivity in ohm meters, a crucial environmental factor. K_M is the spacing factor for mesh voltage, accounting for the physical arrangement of the grid. K_I is a corrective factor that adjusts for the specific geometry of the grid, including the presence of rots. I_G is the grid current, representing the fault current flowing into the grounding system. Finally, L_M is the effective buried length in meters, which varies depending on the grid's configuration. For grids without ground rods, or with only a few scattered rods, L_M is simply the sum of the total length of grid conductors, L_C, and the total length of ground rods, L_R. However, for grids with ground rods located in the corner, along the perimeter, and throughout the grid, a more complex formula for L_M is used. This formula involves L_C, L_R, and a term incorporating the square root of L_x squared plus L_y squared, where L_x and L_y are the maximum lengths of the grid in the x and y directions. The spacing factor K_M is calculated using a detailed equation involving the spacing d, the depth h, and the effective number of parallel conductors n. D is the spacing between parallel conductors, typically measured in meters. The diameter of the grid conductor, d, is also a factor, often specified in millimeters and converted to meters. The depth of the ground grid conductors, h, is another important variable in the calculation. The effective number of parallel conductors, n, is a complex parameter that depends on the grid's overall structure. This factor n is derived from n_A, n_B, n_C, and n_D, which account for different aspects of the grid's geometry. n_A is calculated as 2 times the total length of grid conductors L_C, divided by the peripheral length of the grid L_P. For square grids, n_B is simply equal to 1. n_C and n_D are typically 1 for square and rectangular grids, simplifying the calculation in many common scenarios. Let's consider an example: a grid with a maximum x direction length of 83 meters and a y direction length of 103 meters. Given these dimensions and other parameters, we can calculate n to be 12.56. With K_II equal to 1 and K_H equal to 1.225, the geometric factor K_M is then calculated as 0.34. The corrective factor K_I, considering n as 12.56, becomes 0.644 plus 0.148 times 12.56, resulting in 2.5. The effective buried length L_M for a grid with 80 ground rods, each 7.5 meters long, and a total grid conductor length of 1,731.28 meters, is calculated to be 2,702.8 meters. Using these values, with a soil resistivity of 40 ohm meters and a grid current of 28,000 amps, the mesh voltage _M is calculated as 352.23 volts. Comparing this to a tolerable touch voltage of 676.4 volts, we find that E_M is less than E_touch, indicating the design is safe. If the design were not safe, redesigning the grid would involve decreasing conductor spacing, increasing the number of rods, or lowering the tolerable touch voltage. These calculations are vital for ensuring the safety and reliability of substation grounding systems, protecting both personnel and equipment. End of part 3. Thanks for watching the video. Please share the video and subscribe to my channel.